Alright, so this is the cylinder optimization problem given for Calculus 220 honors. And basically we're going to be taking a problem that was given requesting the optimization of a cylinder and figuring out what the best price is with relation to the size of the container. So in this problem they give us a few constraints. So the container has to be constructed in sections. So there's going to have to be 3 portions of this container. The container is going to hold 7,200 cubic feet at max, but has to be scalable to pocket size. So we want to make sure that we're able to scale this, which the cost function will allow us to do. Now they also give us constraints with this cylinder. They give these here, so the sides are going to be 20 per square foot, the caps are 35 per square foot, and the welds are $1.50 per square foot. So with this, we should have enough information to create a cost function. So we're going to start here with our 3 sections of cylinders. We have the end caps, and then we have the 3 sections. So we need to find the area for the caps, we need to find the area for the cylinders, and we need to find the distance for the welds. Now, we know that the area for a cylinder is going to be 2 pi radius times height, and we need 3 of these. We also know that for the area of a circle, here we have pi r squared. And lastly, we know that the circumference of a circle is going to be 2 pi times radius, and we need 4 of those to connect the caps to the cylinder and the cylinders to themselves. So with this, we have pi r squared plus 2 pi r and plus 2 pi r h. Now we know we need 2 for each end cap, so we need 2 of these, and then we need 4 of the welds, and we need 3 cylinders. And this is just the beginning of our cost function, because we also have to take into account the cost. So let's go ahead and do that. So to start with our cost function, we know that we have 6 pi r h plus 2 pi r squared plus 8 pi r. And now this accounts for the welds. So we've got the welds here, we've got the end caps here, and we have got our cylinders right here. Now we need to account for the cost, and if we look back here, we can see the cost was 20 for the sides, 35 per square foot, and $1.50 per foot. For the cylinder, we have 20 for the side, so 20 times 6, we're going to have 120 pi r h plus, now we have the end caps here, and that was 35, so we're going to have 70 pi r squared, and finally for the welds it was $1.50 per foot, so times 8, that's going to give us 12 pi r. So this is the beginning of our cost function with respect to r. Now we do have a minor issue here because we can only differentiate with respect to one variable, which we are wanting to differentiate with respect to r, but we have this h variable here. So how can we get rid of this? We know that the volume of this cylinder is going to be pi r squared h, which is obviously very similar to pi rh. We're just squaring the radius to get the volume. Now this function here is accounting for 3 separate containers. So the total volume is going to have to be multiplied by 3. So this equals our total volume. Now with this, we can rearrange and get H by itself. So that's going to look like H, just do a little algebra, and we have 3 pi r squared with the volume over the top. So now we can rewrite this expression to give us our cost function with respect to one variable. So now we want to find our full cost function, which will be cost of r equals 120 pi r, and now here we enter our h equivalent, and then we add end caps, and we add the cost for welds. So this gives us the full cost function with respect to radius. Alright, so now that we found our cost function, we're going to go ahead and clean things up a little bit. And so we can find our derivative. So we know that our cost function, as before, was C of R equals 120 pi R V over 3 pi R squared, and then plus 70 pi r squared plus 12 pi r. Now we can see here that we can do a little bit of simplification with the multiplication here. 120 and 3 will reduce. Pi and r will cancel. So this will give us a little bit more simplified version of this function, which is going to be 40v over r plus 70 pi r squared plus 12r. Alright, so now that we have this simplified form, we can go ahead and find the derivative to optimize the cost of this cylinder with respect to the radius. So the first thing we'll do, let's rewrite this to make this a little bit easier to manage. So 40v, and remember the v is actually being used as a constant in this. And so when we take the derivative, 40v r to the negative 1 is going to be negative 40 v r to the negative 2 plus 70 times 2 is going to be 140 pi r, and then 12 pi r will just simply be 12 pi. And this gives us our derivative, which we will set equal to 0. So now that we have our derivative, we can actually solve for this and figure out what our optimized cost is going to be with respect to the radius of the container. So the only thing we need to input is our volume value here. So let's go ahead and set volume to the maximum constraint they gave us at the beginning, which is 7,200. So with that, our derivative is going to be C of R is equal to negative 40 times 7,200 over R squared plus 140 pi R plus 12 pi. And now we just have to set this equal to 0, and we can solve. Now what this gets us is R at 0 is going to be equal to 8.655 feet. And if we plug this number into our original function, we will see that cost at this radius is 50,075. Now this can be seen on a graph right here. So we can see that at the derivative 0 point, the radius is 8.655, and at 8.655 our cost is at its minimum on the graph at 50,075. So what this allows us to do is utilize this function, and I was able to plug these the function into MATLAB and program the output. So it shows me my derivative and my cost function here, and we can see if we increase down here, if we increase the volume of the tank, we can see that the cost and radius increase with that, but we can see kind of how this cost function grows. But throughout, once we put in the total volume, we can see that we're able to achieve an optimal cost by associating our derivative with the original function. Now, something else I was able to do was to show this graphically with a 3D version of the cylinder, so we can kind of get a sense of what this might look like and how it might act when changing the volume. So if we change the volume on this, it's going to change the height and radius. And you can see the container will obviously grow in size with the volume increase, and we can kind of see the relationship between that change. So just kind of a fun way to visualize the change that's actually happening with this. And that is how you do a cost optimization.